where we finished off this lesson. We were talking about this model, the fetch, decode, execute model, which was a model. A model is something abstract, something simple that can be used to explain something more complicated. And so the simple thing that we're trying to, the complicated thing that we're trying to explain simply here is how a computer should work, how our modern computers should work. And this model was produced by Van Neumann. And the model has an input, output. I should actually make this a little bit bigger, so maybe it's a little easier to see. But you know, you can look at this at any time on your on D2L, right? So this document's there for you. You can look at it on D2L. So we have an input and an output, and we have a central processing unit. The central processing unit is controlling the sequence of the commands that are happening. In other words, when a command is going to be executed, and it also is going to. The arithmetic logic unit in the CPU is actually going to do the calculations and going to do the comparisons of this is bigger than that, or this is equal to that. So our arithmetic, that's the logic part of the arithmetic. And then there's going to be some temporary memory. Now notice in this assembler code, which is the first sort of written programming language, the addresses of are mentioned in the code. Well, the addresses that they're talking about there are the addresses in the memory unit. So we have a lot of different memories in our computer, and the one that's closest to the CPU is called registries. But then we have our random access memory as well. But all of those memories have an address. We can access information that's stored in memory by its address, and so that's how that first programming language would be. It would have to specify the address of where things were and where you're going to put things. And so that was, it was kind of hard to write programs like that. You had to write a lot of commands to get anything done, right? So even just to get a piece of data, you'd have to say where the data is and what you're going to do with it. And that basically is built into this idea of fetch, decode, execute. Fetch means to get something from our memory. Decode means to process it or to understand it in the programming language, and execute would be your processing. And then after that, we see we might do some output. Right, so that was the idea of a stored program by von Neumann. So once we had this, so historically speaking, with von Neumann's architecture, basically all computers since the 1940s have followed that model, are using that model. And so since they're using that model, we can program them expecting that to be the truth. So expecting to be able to fetch a command out of the memory, decode the command, and process the command and do something with it. So we got the architecture designed that way. We can make the programs work that way. And so these computers, the UNIVAC, for example, were built based on that model of input, processor, memory, output, so that we could do the fetch, decode, execute. AO is an assembler type language, and so it had commands like this. These would be the language that was first used in these very early computers. So I call that assembler, or it's also referred to sometimes as a second generation language, where the first generation was, working with wires and solder and, little jumper things. So to do programming on the very early computers, you would be doing sort of physical engineering. So when we got to this second generation, we have the proper model, and all of our computers are built with that idea of an input, processor, memory, output, so that we could then have programs that would work with that. So when we're saying add R1, R2, R3, our R1, R2, R3 are going to refer to some memory address. And we still do something like that with our more modern programs, but these R1, R2, R3, though they are a memory address, we actually will have a variable assigned to them. So a variable will take a memory address, and whatever is stored in there can be fetched by calling its variable name, and we do that. Right. So Grace Hopper, we talked about in an earlier slide. She actually wrote programs, right? So she was involved in that first language, the assembler language, but she was also involved in the next generation languages, which we called third generation languages, which are structured programming languages. So COBOL, a lot of other languages of that third generation, things like Fortran. I don't know if you've ever heard of these. COBOL, Fortran, C programming language is a pretty old one, Pascal. Those were the programming languages which were a level above this, where you didn't have to actually sort of say add this at this memory position. We could just use the name of a variable and do processing with it. It was a bit easier to conceptualize. So you could write more complicated and more powerful programs. So yeah, there's Dr. Grace Hopper, Rear Admiral Dr. Grace Hopper. So she had a pretty high rank in the American Navy, and she invented or designed this programming language called COBOL. COBOL was a programming language. I learned how to write COBOL programs when I went to university and studied computing. So it's been around for a while. I mean, I think it was invented in like 1944. I was thinking it was more like 1950. So she was working with them, but I think it was about by 1950 that she actually got the COBOL to be sort of stable, could be used. Now the debugging, we see a picture of this moth here. She actually invented this term. Do I want to say anything else more about COBOL? COBOL was the programming language that was used by businesses, as opposed to a scientific programming language like Fortran or C. So engineers would use Fortran and C because it's very mathematical, had very nice mathematical things, and it was pretty short languages to work with. COBOL was pretty wordy, but that meant that with the COBOL programming language, a business person without too much training could look at the program and kind of understand what it was doing in business terms. And so it was a pretty good language. And because of that, it lasted for a long time. So as I was saying, I studied COBOL when I started studying computing, which wasn't until the 1980s. And so they were still using COBOL in banks and governments and things like that in those days. All right, so I mentioned that Dr. Hopper, Rear Admiral Dr. Grace Hopper, she's working in the Navy, and you might say, well, why does the Navy care about business computing? Well, particularly the way that the United States military runs their operations. And they do a lot of wars. They've been doing a lot of wars. I think we have to admit that. And so they have a way of doing it. And their way of doing it really does focus on getting materials and people. I was going to say men, but they use a lot of women in their army now too. But getting materials and people to a particular place at a particular time in enough quantity. And this is particularly obvious for example, in World War II, when they were fighting in Europe. It was obvious to all of the other armies when the Americans would be there, they had all this food and stuff. They had a lot more than everybody else because that's what they did. They spent a lot of time just making sure they got all that right. We call it logistics, I guess you'd say. So they actually focus on that a lot. They have big warehouses. They move things in the right amount of things at the right time. Wasn't a new idea that the Americans came up with. That's the way they've been fighting wars forever, basically. And but they did perfect it pretty well. And so to the point where they, as I said, they had very high-ranking officers looking at writing computer programs and using computers so that they could get everything to the right place at the right time. Now, she actually invented this word called debugging too. And that's because those old computers that they were using, they produce a lot of heat and they produce a lot of light and they attracted insects. A moth will fly into light. I don't know if you've guys, there's not many moths around here, but if you have a light outside, moths will fly into it. Other insects will as well. And the problem with the moths with her original computers is that they were flying into the computer and they would cause a short circuit so that the wiring would be broken at that point and the computer wouldn't work anymore. And so she'd notice that there was something wrong with the computer. She'd go and inspect and she'd find that there was a bug. So bug being the generic word that we use for almost all insects. So a bug can be just any insect, but she'd notice that there was a moth bug stuck in the computer, and that's where the computer, the electrical short was, which stopped the computer from working. And so she'd have to go in and clean the bugs out, and then replace the broken component. And so she called that debugging. Does that make sense? Now we refer to debugging. We'll refer to it as what we're doing to our computer programs. Now we say that a bug, obviously it's not an insect, but a bug will be some error in our program. So it could be a syntax error, which means that the program won't compile and run. The computer just sort of crashes, won't let the program run. Or it could be what we call a logic bug, in which case the computer program runs, but it doesn't give the result that you were expecting, because it doesn't have the right logic in it. You guys will have both of those kind of bugs nowadays. And so the type of debugging that you'll do is you'll be trying to find errors in your programs and correct them. And we could have a degree on that almost, on debugging. There's a lot of ideas and strategies and tactics to help you to sort of do debugging. There's tools that are built into your compilers and interpreters to help you to find errors or bugs and to remove them. And so if you're going to be a software developer, at some point you'll get quite good at that. You'll get quite good at noticing where errors are and very quickly fixing them. And so you'll be a debugger, and you'll know all about the debugging tools. So we've got some other things here. The integrated circuit. I think I mentioned the space race to you guys. Did I? Sorry if it sounds like I'm not sure, and that's because I teach 4 sections the same, and so I'm giving this lecture 4 times. So I'm not exactly sure what I've said to you. I know what I've said, but it might have been to another class. Yeah, the space race, where integrated circuits sort of come in, is you can get a lot of computer circuitry onto a very small space on a silicon wafer. Silicon wafer, when we say silicon, we don't mean the silicon that you squeeze out of a tube. What we mean is silicon dioxide, which crystallizes and actually is much of the surface of the earth is silicon dioxide. Now, I don't think I mentioned this to you. You tell me if I told you this, because I know I told it to some other students. If you studied geology, the structure of the earth, you'd know that the center of the earth is very hot and it's molten under a lot of pressure. Actually, it's so much pressure that actually the very, very center of it doesn't behave like a liquid, even though it's at that kind of temperatures. But the center of the earth, because of gravitational forces, what you've got is, if you've got a mixture of different elements and compounds, etc., the heavier ones will go to the center if they can move. And so if you've got sort of liquid, and there is a lot of liquid in the middle of the earth, then those things can move. And so the earth at one point was all very hot and liquid on the surface. The very heaviest things went towards the center. So the center of the earth is this sort of heavy metallic, sort of heavy metals and iron and things like that. Iron's not a heavy metal, but other metals are sort of in the center there. The lighter stuff floated to the top. Now, lighter stuff would be compounds. One of those compounds was silicon dioxide. So silicon dioxide, it came to the top. And that's what our mountains are, and that's what our rocks are that were the original sort of rocks of formed by heat from below, as opposed to the sedimentary rocks. I mean, if you find calcium carbonate, marble, that's not silicon dioxide. But your rocks that were sort of came from below, that were your igneous rocks, they have a lot of silicon dioxide in it. So the point that I'm trying to make is silicon dioxide is very common. It's not hard to find it. Go down to a sandy beach, as long as it's not a coral beach, or as long as it's not a beach that has a lot of shells on it. A lot of that will be silicon dioxide, that sand. Now, having said that, right, in Qatar, I do notice when you pick up that sand, it's pretty calcium carbonate. I mean, this must have been below the ocean at some point. So it might not have as much silicon. So silicon dioxide is very easy to find. All you have to do is purify it. And then once you've purified it, then you adulterate it again by mixing in some germanium oxide and other semi-metals. And by doing that, you can make a semiconductor, which is, depending on the the electricity that's applied to it, you can make gates turn on and off. So by making gates turn on and off, you can do what was done by those heavy vacuum tubes. Remember we showed the picture of the heavy vacuum tubes in the original computers? You can do that in a very, very sort of microscopic at an atomic level. And so with very little amount of electrical potential, in a very little space, you can have a computer gateway. And so you can actually get billions of gateways on a small little silicon dioxide wafer. Now, silicon dioxide, because it's so abundant, it's not expensive. The purifying process is going to make that wafer a little more expensive. And actually, the design of the integrated circuit will make if you do it at a 1-by-1 basis, they would be expensive. But what's happening now is the engineers will design an electronic circuit. They use special electron micrography. That's like an electron microscope, except for not just looking at things, actually drawing things at an electron level. And they do this in a factory and sort of just make millions of them. And that brings the price down quite a bit. So we have very, very powerful technology, electronic technology, which isn't that expensive because the materials are not expensive. I mean, the expensiveness is in the design, but if you make enough numbers of them, then you can sort of make that a cost which is spread over many. So Intel, you've heard of Intel? They were one of the first ones that were sort of coming up with this technology. I mentioned the space race because if you can have a computer technology that's that small, it weighs a lot less, so it doesn't cost as much to get it up into space. And so that the United States government was giving companies like Intel a lot of money so that they could come up with these designs and come up with this technology so that they could have much smaller and lighter computers. And that resulted in the transistor, and it resulted in the integrated chip. So the integrated circuit chip is now everywhere. Everything that you have has integrated circuits in it. I'm pretty sure my watch has it, my phone has it. You open up any circuitry of any time, you'll look in there, you'll see a board of some kind, and you'll see some chips. And they're not expensive. You're buying things that are a couple of bucks. I mean, 10, 15, 20 reals of stuff which has got a lot of circuitry in it. So for example, your thumb drive. I don't know if you've ever broken a thumb drive and look inside, you'll see integrated circuits in there. So I mean, they're pumping these out of these factories. Now, Intel was a company, it's either in California or Texas, but they originated this kind of ideas and the manufacturing there. But the manufacturing pretty soon went to Taiwan. Taiwan at one point very recently was making like a huge proportion of all the microchips used in the world. But they're also being made in Malaysia, Thailand. China is making a lot of these things now. And so that's because they have cheaper manufacturing. That's brought down the price of that quite a bit. So as this says, you can get onto a single chip as much as 48 billion transistors. And so that's a lot of circuitry on a little chip, which the actual raw materials of are very cheap relatively. Now, I don't want you to get the wrong idea that we can just make a computer out of silicon dioxide. That's not true. You have to purify the silicon dioxide to make the wafers. Then you have to make the chips, which are going to have gold and silver and other metals involved, and some plastic. You're going to use some rare metals, which are hard to find. There's only a few countries in the world that produce these rare metals. So there is some expenses in it, but the actual basic wafer chip is made of mostly silicon dioxide, which isn't expensive. All right, so that brings us to this thing. We store things in the memory. So think back a few seconds ago, we were talking about the von Neumann architecture, and it has the processor and it has the memory. So in the memory, how do we measure it? A computer uses binary. What does a computer use binary? Because the gates are on and off, on and off, on and off. So how do we do on and off? We refer to it using only two numbers, 0 and 1. So you can think of a 0 as being off. You can think of a 1 as being on. So that's the basis of our gates in our computers. It's on or it's off. It's on or it's off. 0, it's 1. And we can build up numbers from this 0 and 1. So we would say, well, so we can translate this from base 2, which only has 2 numbers, to base 10. Base 10 has 10 numbers. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we can go from there. But with base 2, we only got 0 and 1. So the number, this number in base 10 would translate to 1. Then the next number would be like this, right? We can't make any bigger in this place, so we have to go to the next digit over, and this would be the number 2. And then the next number after that would be this. That would be the number 3. Then the next number after that would be that. That would be the number 4, right? Then the next number after that would be that. That would be the number 5, the number 6, the number 7, and the number 8. You seen that kind of thing before? That's base 2. So this is the number 8. This number here would be, the number 1 would be 2 to the raised to the power of 0. This is 2 raised to the power of 1. This is 2 raised to the power of 2. And this is 2 raised to the power of 3. And if we look at this, 2 raised to the power of 1 has 1 0 after it, right? 2 raised to the power of 2 has 2 zeros after it. 2 raised to the power of 3 has 3 zeros after it when we, anyways, I don't know if you find that interesting. It might help you because you're going to have to do binary to decimal conversions. You'll learn that in math. We'll also talk to you, we'll learn it a bit in this course. So this is binary. This is decimal. Base 10, we say decimal. Well, why do we call it decimal? Dec, Roman Latin, stands for 10, right? 10, decade, 10 years. So we use that. So here's some rough translations. 2 to the 10, 2 to the 10 would be 2 times 2 times 2, 10 times. Because 2 to the 3 is 2 times 8 is 2 times 2 times 2, right? So that's 2 times 2 times 2, 10 times. And it roughly equates, so this, the wavy line means, doesn't mean equal, it means equivalent to, roughly equivalent to, approximately equal to 10 to the 3. We know that 10 to the 3 is 1,000. So 2 to the 10 is approximately 1,000. Well, what 2 to the 10 is actually is 1,024, because if you go 2 times 2 times 2 times 10 times, 10 twos times each other, it actually comes out as 1,024. And if you did that 10 more times, that would be a megabyte, right? So 1,024 times 1,024 would be what we call a megabyte, which is approximately 10 to the 6 or approximately 1 million bytes, and etc. So gigabyte is a fairly standard number that we talk about, that we use, right? So giga meaning billion. We talk about our processors, like in our phones and our computers. They're working at about 2.4 gigahertz. A hertz being a cycle in a second. So in every second, we're running the computer cycle about 2.4 billion times in every second. So that's a gigahertz, whereas a gigabyte, a byte is a unit of memory space. A byte is actually 8 to 10 bits, where a bit is either this or that. And so we make bytes up, like an 8-bit byte is going to have numbers that can go somewhere between 0 to 255. Now, why from 0 to 255? Because 255 is 1 less than 256. 256 is what? It's 8 bytes, 8 bits in a byte. All right, so the next couple of points are about the fact that computing has increased in power, not in a straight line way, but in a sort of in a exponential way. That is that the slope of the curve of increase is more than 1. Now this was talked about by this guy Moore, who worked for Intel Corporation, and he noticed he had an empirical observation. An empirical observation means that he didn't make a theory, what he did is he looked at what he saw and he recorded it. And so that's empirical. When scientists do experiments, we call that empirical evidence, when they go out and gather evidence, rather than when they write formulas or produce theories. Then that's theoretical. This is empirical, means we actually measured it. So he actually measured it, and what he found was that, about every 18 months, the bang per buck, we could put it that way. All right, how much power in computing do I get for the same dollar? That was like doubling. And so that doubling could be that I get double the amount of memory for a dollar, or I get double the computer speed for a dollar. And so he recorded that, calling it Moore's Law. I'm going to run out of time on my video in a minute, in a few minutes, 10 minutes actually. So when that happens, we'll take a little break. All right. So that's coming in about less than 10 minutes, I think. So we've got a couple of graphs a bit later on that I'll show you related to that. One of the big things in computing that made it more accessible to sort of like everybody, and was brought to us in the first place by Steve Jobs in his company, Apple, when they produced the Macintosh in the middle of the 1980s. And so this represents a screenshot, I guess you could say, of an Apple screen at that time. The idea being that we could draw things, we could do things in a more intuitive. Intuitive means that you could look at it, and without having specific instructions, you could probably figure out how to do it. That was the idea that Steve Jobs was having. Let's make computing intuitive, make it so that kids can do it. That they'll just sit down and, yeah, I can do this, I can click this, I can click that. It wasn't like that before. And let me show you what it means. What it was like before is, so I have this thing called a command prompt. This is how the first personal computer that I ever sat down to, this is all we had, right? You'd sit down and you got a screen like that. Now, what do? Well, you actually have to know some commands. You got no mouse, you know what I mean? You just have to know some commands, and, you start out with your basic commands. So I do a dir, which basically shows me what are all the folders in the directory where I now am. And some of you guys will do some networking. And so we have a bunch of networking commands that we can do there. This is telling me what is the address of my computer. And it's telling me what router IP address I have as well. So, I mean, that's all very interesting. If you happen to be going to do networking, we still do that. That's why I have the command there. But back in 1980, that's all you had, right? Before we got Macintosh, that's all you had. So people had to be really interested in computers to do it, right? It wasn't sort of just sit down and I do something. You'd actually have to look at a handbook somewhere, or have somebody tell you, or read something in order to do a computing. You sit down at a computer. Yeah, well, what do I do now? It says A. Yeah, you'd have to. Unlike our computers now, when we turn it on, we got a bunch of sort of cues that we can go, oh, well, look at that. Oh, look at that, Google Chrome. I double click on it and I get a browser opening. It's much more intuitive. It's much more obvious what we have to do. And you probably, I don't know, but maybe the first time that you sat down to a computer, you started doing stuff without anybody telling you, right? You could just do stuff because you could just click this, click that. Pretty soon some things happen. And actually, I do talk too much. I'm sorry about that. But what we notice about children as opposed to adults, children, if you sit them down in a room with just a bunch of random stuff that they've never seen before, they'll pick it up and they'll prod it and they'll test things. They're very experimental. That's what children are. Whereas adults, we might look at it and we'll think about it. So if you have a graphic user interface, kids will just do it, right? They'll start clicking on every button, and pretty soon they'll figure out what's going on. And so that was a great thing for sort of bringing computers to everybody. Kids would certainly get onto it. Now, the only thing here is sort of the copy, right? Let's do what Apple did. And so IBM realized that they had to sort of compete with that type of computing experience. They actually developed their own operating system called OS/2 and their own computers that sort of ran that operating system. I think specifically to compete with that. So they had a graphical user interface as well. Microsoft introduced their own graphical user interface all around that time. And we've got the sort of great granddaughter or son of that, which is Windows 10. So Windows 1 didn't look all that great, but you used a mouse and you had a few little images. And now we've got sort of Windows 10, which is kind of a lot better. All right, so the GUI, these guys here relate to that. As it says, you might have heard of these guys, Steve Wozniak and Steve Jobs and Gates, Bill Gates, and his partner, Paul Allen. So Paul Allen and Bill Gates, they're Microsoft. When Bill Gates actually still making money out of Microsoft because he's an owner, right? He owns a lot of the shares and it's a publicly traded company. So he's still got a lot of money from that. But he doesn't run the company anymore. So not for a long time. And so Paul Allen took over after him. Poor Steve Jobs died before he should have. What I mean is like 50 or something. But yeah, very interesting there, right? You can have people who are really smart, but also kind of really strange. So, I mean, you know, he had some strange ideas, right? So he got cancer, and rather than go to the hospital, he thought that he'd try some metaphysical sort of ideas. I don't know, drinking wheat juice or something. And New Age, I don't know. Anyways, he didn't go and get treatment, and he died probably before he should have. And so that's kind of sad because and other things about him, right? So as I said, you can have people that are really brilliant, but they're not perfect. I mean, most people that worked for Steve Jobs said he was like impossible to work for, you know, shouting at people and sort of just really not a nice guy. Bill Gates also, a lot of people, you know, we think he's a great guy, but not so much. I mean, what I mean is he drove a lot of his competitors out of business, doing what we would call in Australia sharp business practices. And that's a nice way of saying stealing, cheating, and lying. Sharp business practice. So he did that, drove a lot of his competitors out of business in not a very nice way, but you know, it worked, right? Made him billions of dollars, so it must have been all right. All right, so well, I don't really believe that. I'm just saying that, imagining what might have been in his head. I don't think it's right to cheat, steal, and lie. Seems to work for some folks. So the first mice were these sort of basic things here. We had a roller in them. That one's like from the 1960s. Now our mice have got lasers in them, so they're a little bit more precise. So they're a little bit better, and they don't wear out as quickly. Now this thing at the bottom there, that it's got nothing to do with mice. I don't know why it's on that slide, but has to do with connectivity. How do we connect our computers together? Well, a really good way to connect them is with some kind of copper wire. And you would notice if you looked on those computers, if you look behind you, you'd see that they have blue wires in this case, which is Ethernet cable. Ethernet cable has these special connectors on them that it's an RJ, we call it an RJ45, but there's 8 wires that need to be sort of connected up to get you connected to whatever device you're connecting. So these wires go into these connectors in the ground, which then goes to a telecoms cabinet in one of these rooms, not very far away. And then they're going to have fiber. You know what I mean by fiber, right? Orito brought fiber to your house, and fiber is very thin cable. And the good thing about fiber is it carries a lot more data. Yeah, it has a much broader bandwidth, we say, than these copper wires. So you can have a lot more data going down that. So we've got fiber going from our telecom closets to a room at the end of this building, and then fiber from that to our entrance point, which is in building 3, where Orito gives us a connection so that everybody here can have internet. So yeah, so Ethernet is basically, we call this Ethernet cable. And you got an Ethernet port at the back of your computer here. And that's how most of us